I hope all of you are doing well. My name is Shriya Bansal, and now we are going to talk about the concept of memory allocation after having already talked about logical and physical address space and dynamic and static linking. So what happens is whenever you have main memory is always divided into two parts, okay? One is the part where your operating system resides, okay? And one is the part where the process is created by the user basically resides, okay? So here we are just going to talk about the part of the memory where the user processes resides, okay? So in that, there are two ways to allocate the memory which is used for user processes. Okay, so we're just talking about that segment. One is contiguous memory location and the second is non-contiguous memory allocation. Okay, so in this video we'll just talk about contiguous memory allocation first. So whenever we talk about contiguous memory location, all the processes are stored in continuous memory location as it one after the another. We don't keep a gap, right? Everything is a contiguous or a continuous manner. Okay. So to basically load multiple processes in the memory, the operating system basically divides the entire memory into multiple partitions for those processes. Okay. So what happens in contiguous memory allocation is that every process is basically contained in a single continuous section of the memory. Okay, in this type of a memory allocation, the entire memory space which is available, it remains together in one place. Okay, which means that the freely available memory partitions are not spread over here and there, okay, all across the memory space. Nothing happens like that, as in some memory spaces are occupied, then some are empty, then some are occupied, and then some are empty again. That does not happen. There is like a big chunk of memory, continuous chunk, which will be allocated, and there will be a another space of memory which will be freely available, and nothing is just spread out over here and there. Okay, in continuous memory allocation, which is a memory management technique, right, where there is a request by the user processes for the memory, user processes require the memory, okay, and then the single section of the memory block is basically given to that process according to its requirement. Okay, and continuous memory allocation is basically divided by, I would say, dividing your memory or partitioning your memory by two different techniques. Okay, the first is the fixed size partitioning, okay, or I would say multiple fixed partition or multi-programming with fixed tasks, or you basically do multi-programming partition with multiple, I would say, multiple variable partition, where you do multi-programming with variable task. Okay, so always remember that whenever you will talk about contiguous memory management technique, it is going to have two things. Okay, it is fixed size partition scheme and then we have variable size partition scheme. Okay, first we will talk about the fixed size partitioning scheme. In the fixed size partition allocation, okay, what happens is the operating system, or let's first talk about multiple partition scheme also, that might give you a better idea. So in multiple partition allocation or variable size partition allocation, a process is selected from the input queue which is trying to get executed, and it is loaded in the free partition. Okay, and when that process terminates, the partition becomes available for other process. Very simple, right? This kind of a scheme is known as dynamic partitioning, and it came into existence, okay, later on when we figured out a few problems that existed with the fixed partitioning scheme. Okay, now in this, what do we do is, since it is variable partition, variable size partition, whenever we are dividing the memory, we do not say that every memory will be of fixed size. Okay, each and every segment of the memory can be of different sizes. Okay, so in variable size partitioning or multiple partition allocation, right, a process is basically allocated, right, and it is not like given the exact same or the specific segment of memory. Okay, here the allocation is done dynamically, where the size of the partition, right, is not told or declared in the start. Okay, and whenever a process basically arrives, a partition of the size equal to the size of the process is created and allocated to the process. So the size of every partition is equal to the size of the process. So in this case, size of the partition is equal to the size of the process. Okay, so here what can happen over here is, this is the memory. Sorry, also this should go over here. Sorry. Let's say there is some, this was the operating system. Let's say there is process P1 came, which required 3 MB. Process P2 came, which required 5 MB. Process P3 came, which require 8 Mbps. So based on the size of the process, the memory is basically allocated in the free region, and when the process terminates, the memory is taken away. Okay. When we talk about fixed partition allocation, in this method, what happens is the operating system maintains a table that indicates which part of memory are available and which are occupied. Okay, initially all the memory is available for user processes. Okay, and it is one large block of memory. This available memory is known as whole. Okay, and when the processes arrive and when they need memory, we search for a hole that is large enough to store this process. Okay, and if the requirement fulfills, then we allocate the memory to that process. Otherwise we keep otherwise keeping the rest available to satisfy the future guest. Okay, while allocating a memory, sometimes dynamic storage allocation problems occur, which concerns how to satisfy a request of of size n, which has like a list of free holes. Okay, so to understand the fixed size partitioning scheme, understand it this way. Okay, first of all, it is also known as static partitioning. Here the size that is taken by each and every memory, each and every process, the size it takes is dependent on the size of the process itself. Okay, whereas in the fixed size partitioning, the system divides the memory automatically into fixed size partitions. Okay, now the partitions may or may not be the same size. Okay, the size of the each partition is fixed though. Okay, as indicated by the name of the technique as well. In this partitioning scheme, each partition can contain only one process. Only one process. Okay, now here there is a problem now, that this technique will actually limit the number of multi-programming or the degree of multi-programming, because the number of partitions decide the number of processes that can be executed parallelly. Okay, more number of partitions, more processes, because every partition takes one process. Okay, now here an example for that would be, let's say here we have a 15 KB of memory. Okay, and it is divided into fixed size partitions. Okay, so what happens is, here let's say you have this, and here what I am going to basically do is, let's say every memory has 6, this is let's say this is 100 MB, and I am making fixed partitions of 10 MB. Okay, so there will be a total of 10 partitions. So that automatically means, first of all, that the number of multi-programming degree basically is 10 over here. You cannot do a multi-programming, right, more than 10 over here. Another problem with this kind of an approach over here is that now let's say what happened was, here there is a processes for 10 MB and there is a process for 7 MB that came. So it will only occupy this much, and this part will remain empty, correct? And here, let's say this is the part, and next process which came in was for 5 MB. Okay, but now every process can have one partition. So here what will happen is 5 MB of storage will basically get wasted. Okay, so what happens in fixed size partitioning is, since the size of every partition is fixed, right, it leads to a problem where there is a wastage of space. Okay, wherein there is a space which can never be utilized, whereas we tackle that problem using variable size partitioning, where the size of a partition equal to the size of the process. So you have everything one after the other, and in between no memory basically gets I would say affected. Okay, so this scheme is very simple and easy to implement. Okay, and here many management, and here the management of this kind of a scheme is very easy. But the issue is that this kind of an approach leads to the situation there where there is a wastage of space between two partitions over here. Okay, and that wastage of space between two partitions is actually known as the concept of fragmentation, which we are going to talk about next after this. Okay, which is basically the concept where a particular piece of memory gets wasted. So first, let's talk about fragmentation, and then we'll come and talk a little bit about partitioning selection algorithms as well. Okay, so first of all, always remember that wastage of space is a disadvantage of fixed size partitioning. Okay, now this wastage of space also can be of two, I would say, different types. Okay, first of all, before that, we'll focus a little bit on fragmentation, right? So fragmentation is basically the name provided when there is a wastage of space, right, in one of the partitioning techniques that you apply. The fragmentation technique is further divided into two parts: internal fragmentation and external fragmentation. Let's first talk about internal fragmentation. Now, it is a problem that occurs, okay, when the process is allocated to a memory block whose size is more than the size of the process, and due to which some part of the memory basically gets wasted. Okay, so here what you can see is the allocated memory may be slightly larger than the memory which was actually requested. So here we saw that the partitioning size was 100, but you actually just needed a space of 80, right? So let's say here the 20 MB of space will get wasted. And this wasted space within a partition, inside a partition, there is a piece of memory which is used and there is a piece of memory which is wasted. That wasted space inside a partition is known as internal fragmentation. Okay, and one method to reduce internal fragmentation is to not keep the size of the partitions fixed, but to actually allow partitions of different sizes. Okay, next is the problem of external fragmentation. Okay, now here what we say is that the total memory space is existing to satisfy a particular request, but it is not contiguous. Okay, so there is like a certain set of memory which is existing. Let's say here, because I told you in fixed size partitioning also you can have partitions of different sizes, but their size is always like fixed. So here let's say you have this memory and you created 3 partitions of different sizes, because that's what internal fragmentation asked you to do to solve the problem. So you basically created a partition, let's say for 8 MBs. Okay, then you created a partition for 10 MB, and then you created a partition for 3 MB, This was for user processes, and here the operating system exists. Okay. Now here what happens was, there was a process which came in for 6 MB. Okay. So you allocated 6 MB to it. Then there is a process which came in for 4 MB. Okay. So you have no option over here but to allocate the 4 MB to this. Then there is a process which came for 2 MB. Now this is the only page where you can let it go. Okay. Now what happens is, here let's say another process comes which is for 8 MB. The problem is that you cannot give, or you cannot basically allocate space to this 8 MB process anywhere. But if you will actually see now, here we had what? 2 MB of space. Here we had 6 MB of space, and here we have 1 MB of space. So total across all partitions, we do have a space of 9 MB available, right? I want to allocate memory to a process of size 8 MB, right? And we can see that in there is actually 9 MB of space available, but that is not continuous memory. That is fragmented across multiple partitions. It is a lot not continuous. Hence, we cannot allocate this memory, this process the memory, although there is actually space available. This kind of a fragmentation or a wastage of space is known as external fragmentation. Okay. So I hope this is clear to everyone whenever we talk about the concept of internal fragmentation and external fragmentation. Okay. So here, remember that external fragmentation basically happens when you are allocating, right? I would say it basically occurs when the memory blocks of variable sizes are allocated to the process dynamically. Because what we're doing is, here a process came, we allocated to it. Here a process came, we allocated to it. Here a process came and we allocated to it. Okay. That is when the concept of external fragmentation kicks in. Okay. With this, one more important thing that we will talk about is the partition selection algorithm. Okay, because as you can see in here, in the concept of variable size partitions, okay, where the partitions have different size, and when you have the processes coming in dynamically. So how do you take the call which partition to go where? Okay, because here you can see that the 6 MB was available, and you had a partition of 8 MB also, and you had a partition of 10 MB also. So how do you take the call of the process of 6 MB to go whether in 8 MB or 10 MB? Okay. For that, we have multiple partition selection algorithms that basically exist. Okay. Because we just read over here that all these available memories are known as whole. Okay. Available memory blocks basically comprises of a set of holes, right, which are scattered throughout the memory. Okay. And whenever a process arrives and it needs memory, the system basically searches for a hole that is large enough for the arrived process to fit in. If the hole is too big, right, sometimes we split the hole also into two parts. Okay. So just for this allocation, for the process to the required hole or the required block of memory, we have multiple allocation strategies which are present. So which we will talk about. Okay. So here we talk about first fit, best fit, worst fit, and next fit. Okay. So first let's talk about first fit. So what do we do in first fit is basically the operating system, there's a process which needs the memory. Operating system starts looking at all the free sections of the memory. Okay. And basically it allocates the first hole or the first partition that is big enough, then the big enough in size, then the size of the process. Okay. So here that is how the allocation is done. For example, if you have the memory like this, here you have the operating system, here you have, let's say, 4 KB of space, here you have 20 KB of space, here you have 1 KB of space, like this is not fair allocation in terms of size. Okay, let's say something like this. And let's say there you have 10 kb of space. So the operating system, there is a process which is for 10 kb. Now the operating system will start from the very first point and it will keep looking. It will see here the process requires 10 kb but there is 4 kb. Not good. It requires 10 kb but it is 20 kb. That means this hole is big enough for the process P1 of size 10 kb and it meets the requirement. Its size is bigger than the size of the process and hence we can basically put the process P1 over in this space. So the first fit that is basically find out, the first hole that is find out, irrespective of the fact which is present later, is the one where the process is allocated. Okay. Next, we will talk about over here best fit first. Okay. So the best fit in this strategy, what we do is we actually search the entire list first. It's not like the first hole we find out which satisfies the requirement, we'll just put it. No. We basically search the entire list first, list of all the holes to find out which is the smallest hole that is big enough for the process. For example, if there is a process P1, there is hole of process P1 of size 8 kb. Then there are holes of size 6 kb, 10 kb, 12 kb and 15 kb. So if the process is of 8 kb and there are holes of size 10, 12 and 15, we would want to put it in 12 so that there is as less wastage of space as possible. So what we do is we search the entire list of holes to find the smallest hole that is just big enough than the size of the process. Okay, so if you take this example over here again, where we have the operating system 4 kb, 20 kb, 1 kb and 10 kb. So if there is a process that will come for 10 kb only, according to best fit, this is the best fit for the process in the memory. Okay. Then we have the worst fit. In the worst fit, the fit actually searches in the entire list of hole and finds the biggest hole that is big enough, right, than the size of the process. Here we actually look the one which is the biggest and not the smallest. For example, if I have this operating system 4 kb, 20 kb, 1 kb, 10 kb and let's say there is also of 80 kb. So what happens in worst fit is that for a particular process, you actually find out the biggest size, okay, for that. So if there is again a process of 10 kb, we will actually put it in the 80 kb block, okay, because it's actually the biggest one, right, biggest hole for the process, okay. So this is what worst fit basically is. Okay, and here you can see next is the next fit, right? So the next fit basically starts at the last hole that was allocated and the process is allocated to the next hole that is big enough than the size of the process. So what you do is, let's say here you did the allocation for process P1, okay, or here let's say you did the process allocation for P1 over here, or like here, let's not destroy this example. Let's take another example. Here we have the operating system 4 kb, 10 kb, 6 kb, 9 kb. Okay, so what you do is, let's say here you applied the algorithm where there was a process P1 for 10 kb. Okay, so what do? You basically find out the best fit, which is 10 kb. Next fit says that if now let's say a process P2 came for 9 or let's say 8 kb. So what do? You don't start from the start, or let's say there is a process which came in for 3 kb. So you don't start looking from the start. Oh, sorry, I did not add it. Let's say here there is a process for operating system and these are there was a process of 10 kb and we allocated 10 kb over here. The next fit says that now if another process comes for 3 kb, don't start looking from the start. Start from where you allocated the previous process and just find the process which is big enough. So in this case, P1 will go over here and P2 will go over here. So you don't start searching from the list from the start again and again. You basically start searching from where you left off. Okay, and you just find a block or a hole which is big enough for the process. And you can see here also, in this case, there are partitions of variable sizes, but here there is a lot of wastage of space as well. And that wastage of space concept is the concept of fragmentation. Okay. So I hope this is clear to everyone and you have understood all aspects of continuous memory allocation as well. In continuous memory allocation, you just try to allocate the memory into continuous sections instead of just spreading the allocation here and there, and everything happens one by one after the other. You divide the memory, either you can divide it into fixed size partitions where every partition is of fixed size. Okay, and there you saw that there was a problem of internal fragmentation. Then what we said was that you keep the size of the partition fixed, but the partitions could be of different sizes, and even that led to the problem of external fragmentation. And then we came up with the idea of multiple partition allocation, or you can say this is known as variable size partition, where there is no dynamically size assigned to a partition. Whatever process comes, it just takes that much memory. The next process comes, it just takes just after that much memory. Okay, and with this we conclude our discussion for continuous memory allocation as well. In the next video we will talk about non-contiguous memory allocation. All right, thank you.